Today we're going to be talking about permutations and combinations. We will be learning the basics and solving some example problems. If you find the video helpful and educational, make sure to like and subscribe. So, what are permutations and combinations? Permutations and combinations are used to count the number of ways something can be arranged, sometimes out of a bigger group. In permutations, the order of the items matters. So, for example, a set AB is different from the set BA. However, in combinations, the order does not matter. So, in other words, a set AB is the same as the set BA. So now we can see the formulas for permutations and combinations. So here we have the permutation formula, and that is n factorial over n minus k factorial. And here we have the combination formula, which is n factorial over k factorial times n minus k factorial. And the notation for permutations is over here, and we say that as n permute k. And for combinations, we see the notation over here, and we say it as n choose k. Another way to write this is n, then a big C, and the k. But the first one is more common when it comes to combinations. So you might be wondering what the exclamation mark in the formula means, and it denotes a factorial. So by definition, a factorial is 1 times 2 times 3 times all the way up to n, and this is said to equal n factorial. There is an exception to this case, which is 0 factorial, which is equal to 1. And we will explore the convenience of 0 factorial being equal to 1 later on in this video. So it's not really that important to memorize these formulas, but the concept behind these formulas is very important. So if you forget these formulas, you'll still be able to apply the concept, and we will see these concepts as we work through some example problems. So now let's start with a very basic example, the standard permutation question, which is how many ways are there to arrange 4 books on a shelf, right? So let's say we have 4 books. We can call them A, B, C, and D, right? These books are distinct. That means there are no repetitions. So A is different from B, B is different from C, and C is different from D. So they're all different. So we start by thinking, how could we do this? Well, we can think of there being 4 spots on the shelf, right? Where one of these books will go in each spot. And once we use a book and put it in a certain spot, we can't have that book as an option for the next spot. So for the first spot right over here, there are going to be 4 choices for which book goes there. It can be A, B, C, or D, right? So let's say I choose B to go there, right? It doesn't really matter what we choose because I'll just create a new way to arrange the books. So then the next spot will only have 3 options. It can only have A, C, or D since we've already chosen B. So let's say I choose A to go there. Similarly, the next spot will only have 2 choices for which book goes there. And the last spot will only have 1 choice. It's the remaining book that's a leftover. So let's say I choose C and D. Right, so that is one arrangement of the books right there. So we can multiply all of these choices together to get 24, which this is really equal to 4 factorial. And that's it. We solved the problem. The answer is 24. So what we did was we said there are different spots in the shelf, and each book can only go to 1 spot. And then we list out how many choices are there for each spot. So now let's go to the next problem to see a similar problem, but a little more harder. So we have how many anagrams of orange are there? So anagrams are basically the number of ways to arrange the letters in a word. So let's say we have one anagram, right? And that anagram could be RANGOE, right? So we want to count all the different anagrams of this letter. So, or this word. And we can think as there is 6 spots. Similar to what we did in the last problem, where we thought there were different spots for the books on the shelf. And since there are not any letters repeating, right? So we can just simply think of there as being 6 choices for which which letter goes in the first spot, and 5 choices for which letter goes in the second spot, 4 choices for which letter goes in the third, 3 for the fourth, 2 for the fifth, and 1 for the last. So this is equal to 6 factorial, and when you calculate this, you will get 720. So that's our answer for this problem. So our approach to this problem was very similar to the one on the last problem. We just assumed there were different spots for the letters, and then we counted how many choices there were for each spot. Now let's look at a slightly more complicated example. The question reads, how many anagrams are there of the word text? So we can start based on what we did in previous problems. We could say, oh, so there are 4 letters, so there'll be 4 spots, right? And there'd be 4 options for which goes first, 3 for the second, 2 for the third, and 1 for the last, to get 24 possibilities. But this is actually false. It's not the right answer. And this is because when we count like this, we count T1, T2, and EX, and the possibility T2, T1, EX as 2 different anagrams. But in reality, the T's are not different. So T1 is the same as T2. So we really just overcounted what we were supposed to count. So now we want to account for that, right? We want to divide by something to get the correct answer. So what we can do here, we see that there are 2 ways to arrange the T1 and T2. So for each correct arrangement of text, there's also one duplicate arrangement because you could just swap the positions of the T's. So by this, we just have to divide 24 by 2 since each anagram of text has a duplicate when the T's are swapped around. So when we divide 24 by 2, we will get 12, which is our correct answer. So in this problem, we saw that it's not enough to just have different slots for the letters and count the number of choices, but we also realized that we overcount when we do that. So what we need to do is divide by the number of ways to arrange the duplicate letters. So now let's move on to our next example. And this problem reads, how many subsets of any size can we make from a set of 5 elements? So let's say we have any 5 elements. So let's say our set is A, B, C, D, and E. Right. So now what we have to do is choose some element from this set to be in our subset. So there are different sizes of subsets we can make, right? So we could have just one element, so for example A, or we could have multiple elements, so we could have 2 elements, so A, B, or we could have 3 elements, which is, for example, C, D, E, or we could have 4 elements, so we could have A, B, C, and D. Or we could have the entire set, which is A, B, C, D, and E. And there is one subset size that we're missing here, and that is when there is an empty set, which means there are no elements inside the set. And that will be a valid subset of this, right? So now we have 6 different sizes, okay? So let's go through different cases, right? So when we select 0 elements, when we select 1 element, when we select 2 elements, we can just go through the different sizes. And by the way, CDE is the same as the set DEC. So that means the order of the elements inside the set does not really matter. So what does this mean? We use combinations. There'll be 5 choose 0 if we choose to only choose 0 elements, plus 5 choose 1 if we choose 1 element, and then 5 choose 2 if we choose 2 elements, and so on. We can have 5 choose 3, 5 choose 4, and 5 choose 5. So now we just have to calculate all of these and add them all up together. So we can use our formula for combinations, which says 5 choose 0 would be 5 factorial over 0 factorial times 5 factorial. That's equal to 1. Then you have 5 factorial over 1 factorial times 4 factorial, and that's equal to 5. And you have 5 factorial over 2 factorial and 3 factorial. That's 10. And similarly, we can do the same thing for 5 choose 3. And for 5 choose 4, we can do similar things. So what I'm doing here is I'm just applying the formula. I'm just writing down exactly what you would have from the formula. And finally, you have 5 choose 5, which is 5 factorial over 5 factorial and 0 factorial. So we have 1 plus 5 plus 10 plus 10 plus 5 plus 1. And when we add all of this up together, we're going to get a final result of 32. So that's the number of subsets we have. Okay, so there is one thing that we should notice here, and we see that 5 choose 2 and 5 choose 3 are really the same because of the symmetry in the denominators, right? 2 factorial times 3 factorial is really the same as 3 factorial times 2 factorial. So what we can say here is that 5 choose K is, wait, let me rewrite that. Okay, so we can say that 5 choose K is the same as 5 choose 5 minus K. Okay, and we can generalize this, right? We can say that N choose K is equal to N choose N minus K. And this is only because of the symmetry in the denominators that we see here and here. You can also see it here, and even here and here. So that's how we get that N choose K is equal to N choose N minus K. Okay, so there is one more way that we could have solved this problem, which probably would have took a little less calculation, and that is, we can just say that for every element in this set, right? For A, B, C, D, and E, each of them has 2 choices. Either it can be in the subset or it can't be in the subset. So like that, we can give 2 choices for A, 2 choices for B, 2 choices for C, 2 choices for D, and 2 choices for E. Because each one can be either in the subset or not. So it has a choice. It has 2 choices. And this is equal to 2 to the power of 5, which is equal to 32. So we have the same answer as before. Okay, that was that problem. Now let's move on to our next problem, and this is the last problem. And it says, how many distinct seating arrangements of 5 people around a table are there if an arrangement is distinct, if it cannot be rotated onto any other arrangement? So basically what this problem is saying is that if you have this table and you have 5 people, A, B, C, D, and E, that are all seated around this table, we could rotate this table just a bit and we could get B, C, D, E, and A seated around the table. But this arrangement will actually be the same as the first arrangement because we're just rotating it and each one has the same people on the right and the left. So now we look at this problem and we say, okay, how do we do this since this is not the same as just arranging A, B, C, D, and E in a line? It's different because you can rotate something and get the same arrangement. So we're really going to overcount if we just arrange them in a line. So what we can do to fix this is we can say there's a table and there are 5 spots, right? Because there are 5 people. And let's say we have the same 5 people again, A, B, C, D, and E. And so here we can just say, okay, the first person, A only has one choice. We're going to fix where A goes in these 5 spots. So let's say A goes here. And now for the rest, we can just sort of arrange them as we would in the line, right? So B has 4 options, C has 3, D has 2, and E has 1 option. And this will account for rotations, right? The rotations won't be counted twice because each time A will have 2 different people on its right and left. So this way we have accounted for the rotation of the table. So now there would just be 4 times 3 times 2 times 1 is equal to 24 ways this can be done. So now we can generalize this too, right? So if there are like n people that have to be seated around a table, how many ways are there to do this? Always we can choose the first person to have a fixed spot. It doesn't matter which spot this is. They only have 1 option and the rest of them can be arranged as they would be arranged in a line. And this accounts for the rotational symmetry of the table. So we can generalize this and say there be n minus 1 factorial ways to do this. So if we had 6 people, there would be 5 factorial ways. If there were 7 people, there would be 6 factorial ways. Okay, that was that problem, and it was our last problem. I hope you really enjoyed this video and learned a lot from it. So if you enjoyed the content taught in this video, make sure to like and subscribe, and let me know in the comments below what topic you would like to hear about next. Thank you.